Okay, we're in the home stretch. I know it's been a lot of material, a lot of algebra. Please separate for me the conceptual things with the sort of nitty-gritty details of the algebraic manipulations and make sure, I obviously want you to be able to do these things algebraically. I think it's an important skill, but please make sure that the larger concepts here are not being lost. So where we left off is, well, we finished. We derived the least squares estimate for slope and intercept in an overconstrained system of linear equations. Yeah? And we ended up with this equation for the slope, and it just, there's something about these things when I get to the end of it, I think, well, does that make any sense at all? And I'd like to just have this sort of sanity check. Now, looking at this, it's not at all clear that you can make sense of it, so well, let's simplify the problem a little bit. Let's ask ourselves, if we only had 2 data points, what would this look like? This is also just a good exercise in doing a little bit of algebra too if you're a little rusty. So I'm going to break this, this least squares estimate of the slope down, assuming I only have 2 points, n equals 1, n equals 2, I equals 1, I equals 2. And then we're going to get to the end and hopefully we'll get some intuition for what this thing is doing. All right, let's go ahead and do it. So if every iteration, every summation here is going to go from I equals 1 to 2. So this first term is x1, y1 plus x2, y2. Good. Next term is minus 1/2, n is equal to 2. And now I've got a product of 2 sums. So what do I have here? So this is y1 plus y2. That's one quantity. This sum is x1 plus x2. That's another quantity right there. Good. And those just multiply each other. Okay, no problem. Good. Let's go to the denominator. I've got the sum of the squares of the x's. So that's x1 squared plus x2 squared. Good. I've got a minus 1/2 out here, and it looks like something pretty similar to here, but it's the x's in both cases. So that's an x1 plus x2, and that, of course, is an x1 plus x2. Okay, I haven't really gotten any insight. I'm looking at that as much as I can, and it honestly doesn't really help me very much. But it also feels like there's a lot of redundancy there. I'm seeing a lot of sort of similar terms, top and bottom. So let me see if I can simplify a little bit. Again, good exercise in doing a little bit of algebra. All right, let's do this. I feel like I want to break this and this term out. So these are nice because they've separated, but these are all mixed up. So let me go ahead and break them out. All right, oops, I advanced one too many. So y1 x1 plus y2 x2 plus y2 x1 plus y2 x2. That's what I've got right there. Okay, everything else is the same. Oh, sorry, nope, and I break this one out. So it's x1 times x1, x1 times x2, x2 times x1, x2 times x2. That's this. x1 squared, x2 squared, those are the inner and the outer, and then I've got 2x1, x2. Good. I feel a little bit better about that because now I can see all the individual terms. All right, let's start grouping a few things together here. Okay, let's see. I've got an x1, y1 here, and an x2, y2 here, and there's another x1, y1 here, and it looks like there's an x2, y2 there. So I should be able to pull those together, yeah? All right, let's see. I've got x1, y1 minus 1/2 x1, y1. That's 1/2 x1, y1. There it is right there. Good. I've got an x2, y2 right there, and I've got a minus 1/2. There it is. Yeah, minus 1/2 x2, y2, so that gives me another half right there. And I don't think I can do anything with these. I've just got an x2, y1, and an x1, y2 right there. Those aren't going anywhere, so we'll leave them be. But I'll bring the 1/2 in. That's nice too, because I now got 1/2 along the whole top term here. Now down here, I also have some similar terms. I've got an x1 squared and an x1 squared, an x2 squared and an x2 squared. So let's start pulling those together. x1 squared minus 1/2 x1 squared, 1/2 x1 squared. Good. x2 squared minus 1/2 x2 squared gives me a 1/2 x2 squared. And then let's see, this is nice. The 1/2 cancels out. So I've got a minus x1, x2. All right, is this any better? A little bit. I feel like we've broken things up a little bit. I feel like we've simplified a little bit. And I feel like there's some relationship between the top and the bottom. So let's see if we can break this down even a little bit more. All right, so first of all, I've got a 1/2 on every term on the top and a 1/2 on every term in the bottom, except for that one. So I can multiply top and bottom by 2. I can get rid of all the halves. I can get rid of all the halves. And then I just get a 2x1, x2 right there. Okay, good. That's good. Now, I feel like we're getting closer, but we're not quite there. First of all, you're getting better when the equations start to narrow like this. That's a good sign. But this looks really familiar to me. x1 squared plus x2 squared minus 2x1, x2. That looks like something that I've seen before. And I'm still seeing commonalities here. I've got an x1 here and an x1 here, and I've got an x2 and an x2 here, so I still feel like I can do a little bit of factoring up top. So let me try to do that. What is the denominator? Well, of course, it's just x1 minus x2 squared. Why? x1 minus x2 squared is x1 squared plus x2 squared minus 2 times the cross product, the product rather, and that's what I have here. So I'm going to factor that out. And as I said before, up top, I've got some common factors here. So let me pull out the y1, which comes from here and from there, and that's, of course, x1 minus x2. And let me pull the y2 out, which grabs the x2 and the x1 right there. Good, so let me make sure we understand that. I've got a common y1 term in both of those. I'm going to factor it out, and then I've got times the product. I've got a common y2 term, and I've got that right there. So why does this help me? Well, let's find out. So what is this? Well, I've got an x1 minus x2, I've got an x1 minus x2, and I've got a x2 minus x1, so I'm close. Well, I can just negate this whole term, so I can just put a negative sign there, and now I've got an x1 minus x2. Good, now I'm feeling really good about this because I've got this common term in the top and the bottom. Good, so all I did was negate that term to get there. Now what do I have? I've got an x1 minus x2, x1 minus x2, and square of that. Well, so I can just I can divide the top by x1 minus x2, and I can divide the bottom by x1 minus x2. That's allowed. And now I get rid of those terms up top, and I get rid of one of the terms in the denominator. And what am I left with? y1 minus x. Ah, this looks really familiar. The difference in the y terms divided by the difference in the x terms. What is that? That is the slope of 2 points. If I give you 2 points and I ask you for the slope of that, it's equal to y1 minus y2, the difference in the y, divided by the difference in the x. So why did I do all of this? Well, first of all, I just want you to have a little bit of exercise in algebra because it's good. But the other is you can see something really beautiful here. When we reduce to 2 points, this makes perfect sense. This is exactly what you would expect it to be, is that when I have a constrained system, it's just the slope of those 2 points. All right, so least squares, a little tedious, I will be the first to admit. We took this gnarly quadratic error function, we computed partial derivatives, we simplified those partial derivatives. We then had 2 simultaneous equations and 2 unknowns. We isolated one of the unknowns, we back substituted into the other ones, we did a whole bunch of algebra to simplify that term, and we got our answers. And as I said in the last segment, that was a lot of algebra to do to just solve the least squares for a line. Imagine you had a plane or a higher order polynomial with lots of terms. You're now going to have to do that over and over again, and it gets a little tedious, and it's not really the right way to do it. So in the same way, earlier on in this part of the class, where we went from the geometric picture to the algebraic picture to the linear algebraic picture, we saw that the linear algebraic picture generalizes very nicely because it creates a formulation that is easy to extend to higher dimensions. And so what we're going to do in the last segment is take everything we've just done, that sort of somewhat tedious algebraic formulation, and formulate it, least squares, in the linear algebraic, and that's going to be where you live when you go to actually do this thing in the wild. All right, we'll pick it up then.